Let's get into what's been shaking up the skies lately because things are getting wild. Between September 23rd and 28th, a jaw-dropping 10 asteroids zipped by Earth, all closer than the moon itself. These weren't old space veterans either. They were brand new discoveries. The biggest one? About 41 meters wide, roughly the size of a full-blown commercial jet. Imagine that flying past unnoticed. That's chilling. Then, just days later, on October 1st, another asteroid decided to make things even crazier. It skimmed by at only 300 kilometers above Antarctica, lower than most satellites. Here's the kicker. Astronomers only spotted it a few hours after it had already passed. Talk about cutting it close. And before anyone could catch their breath, yet another object, dubbed 2025 TQ2, zipped past the North Pole just 3,000 miles above the surface. Space traffic is getting out of hand. Even the European Space Agency had to step in. They confirmed that several of these little wanderers passed through the very zone where the International Space Station orbits. That's terrifying. It's a reminder that near-Earth space isn't empty. It's turning into a cosmic highway packed with unpredictable visitors. Amid all that chaos, new comets, asteroid close calls, and even the Interstellar Traveler 3I Atlas flying by Mars. There's one particular object that's making scientists sweat, a so-called city killer asteroid that suddenly switched its target. Once feared to be heading for Earth, it now seems to be setting its sights on the moon. Its name? 2024 YR4. And trust me, astronomers are paying attention. When it was first detected back in December 2024, its orbit immediately raised eyebrows. Early calculations showed a 3.1% chance of hitting Earth by 2032. That might sound small, but in space terms, it's enough to sound every alarm. At roughly 55 meters across, it falls right into the city killer category, big enough to unleash megaton-level destruction if it ever struck our planet. Months of follow-up tracking gave a bit of relief. Earth was officially out of danger by early 2025. But what came next shocked everyone. Those same calculations showed that while Earth dodged a bullet, the moon might not be so lucky. The odds of it smacking into the lunar surface now stand at around 4%, and in orbital mechanics, that's huge. If 2024 YR4 actually hits, it could blast out a crater hundreds of meters wide, throwing millions of tons of debris into space. Scientists say some of that debris might even end up hitting Earth's orbit, potentially increasing the number of tiny particles around our planet by 1,000-fold. That could spell serious trouble for satellites, communication systems, and even the International Space Station. That's why planetary defense experts are already hard at work figuring out how to stop it. The first idea on the table, deflection. NASA's DART mission did something similar back in 2022 when it smashed into a small moonlet named Dimorphos. The test worked. It nudged the rock off its orbit, but it came with a surprise. The impact launched a swarm of boulders into space that no one saw coming. Now the same question looms: how do you stop something as unpredictable as 2024 YR4? The truth is, we don't even know its exact mass yet, and that's a huge problem. Push too little, and nothing happens. Push too hard, and you could send it spiraling toward Earth instead. If a perfect deflection isn't possible, scientists may have to consider a far more explosive option: destruction. One plan suggests slamming it with a high-speed kinetic impact to break it into smaller, harmless chunks. But the more controversial backup plan, a nuclear blast. Yep, a study from September 2025 claims that a 1 megaton detonation, if done at just the right distance, what scientists call a height-of-burst explosion, could completely vaporize the asteroid no matter its size. But detonating a nuclear device in space is no small decision. The last time humans did it was back in 1962, during the Starfish Prime experiment, and it literally created artificial radiation belts and knocked out satellites. Space might be vast, but when rocks start aiming at the moon, or worse, back at us, it suddenly feels a lot smaller, doesn't it? Any future nuclear space mission would take insane levels of global teamwork. We're talking every major space agency on Earth moving as one, because under the Outer Space Treaty, it's illegal to place nuclear weapons in orbit, even for defense. So for now, no one's pushing that button. Instead, scientists are using 2024 YR4 as a kind of test case, a cosmic simulation for how humanity might react when the threat isn't aimed straight at Earth, but lurking dangerously close. Statistically, there's still a 96% chance the asteroid completely misses the moon and drifts harmlessly into the dark. But even if nothing happens, this situation is gold for researchers. It helps them understand how fast we can spot a threat, how well we can organize a planetary defense response, and maybe most importantly, how accurate our space math really is. And sometimes, those lessons come with a twist. Remember NASA's DART mission? It was supposed to just nudge a little asteroid, not throw chaos into the solar system. Instead, it ended up blasting hundreds of boulders into space, turning a calm experiment into an interplanetary fireworks show. But before we break that down, a quick word from today's sponsor, Squarespace, the one-stop platform where creativity meets simplicity. With their AI-backed design intelligence, you can create your own digital identity in minutes. Their tool, Fluid Engine, lets you drag, drop, and customize every corner of your site. No coding headaches. Plus, Squarespace comes loaded with analytics, so you can instantly see who's visiting your new page. Now back to the science, and a warning from fiction that still hits hard. In Michael Crichton's Jurassic Park, Dr. Ian Malcolm famously said that nature doesn't always play nice with math. He broke it down into two types of systems, linear and nonlinear. Think of linear systems like cruise control on an empty highway. You tap the pedal, add 10 kilometers per hour, and boom, the speedometer goes up exactly 10. Simple, predictable. That's the easy kind of math. But then come the non-linear systems, the ones that don't play fair. Picture a bone-dry forest after a blazing summer. One tiny ember drifts off a campfire, catches a patch of grass, and suddenly the whole hillside explodes in flames. One tiny cause, an unstoppable, massive effect. That's non-linearity in action. Small changes that spark huge consequences. Keep that idea in your head, because it's about to get real. In 2022, humanity tried something bold. We literally punched an asteroid. Not to destroy it or mine it, but to answer a question that sounds like it came straight from a late-night Reddit debate. If we hit an asteroid, will it move? That experiment became known as DART, the Double Asteroid Redirection Test. The target, a little moonlet called Dimorphos, about 50 times smaller than Mount Everest, orbiting a larger rock named Didymos, roughly 11 million kilometers away from Earth. Engineers began with the basics. Pure physics. Momentum equals mass times velocity. If you know the spacecraft's weight and speed, you can figure out exactly how much force it delivers when it hits. Add that push to Dimorphos, and in theory, you can predict how much quicker it should orbit around its parent asteroid, Didymos. Scientists expected a modest shift, maybe 73 seconds shaved off its orbit. But when DART hit Dimorphos head-on, what actually happened stunned everyone. The orbit didn't shorten by seconds, it dropped by 33 whole minutes. The punch landed harder than anyone imagined, and it changed how we think about deflecting asteroids forever. That's 25 times more than scientists predicted. Wild, right? You'd think, well, hey, that still sounds like a win for planetary defense. But hold up. Space doesn't hand out neat little victories. What happened next turned out to be way more complicated. 2 years after the DART impact, astronomers went back to study the aftermath, and what they found was jaw-dropping. The test didn't just move an asteroid, it accidentally unleashed a swarm of boulders into space, and not just a few pebbles either. Images from LISIACube, the suitcase-sized satellite that trailed DART, captured the chaotic scene just minutes after the collision. A new study by astronomers from the University of Maryland revealed something shocking. Instead of a neat cone of fine dust like they expected, they saw a ragged halo made up of more than 100 massive rocks. Some were as small as loaves of bread, but others were the size of compact cars. And they weren't floating gently away. They were sprinting through space at over 50 meters per second. When researchers tracked their movements, they realized these ejected rocks carried 3 times the momentum of the spacecraft that hit the asteroid in the first place. That's insane. The math didn't just add up, it exploded. See, the original plan behind a kinetic impactor like DART is simple. Hit something hard and fast, and it moves. But those rogue boulders changed everything. The debris didn't just fly off. It acted like a second punch, delivering an extra shove that was nearly as powerful as the first impact itself. That means the true power of DART came from a 2-stage event. The initial strike, followed by a violent, high-speed burst of rock fragments. And it gets even stranger. Those boulders weren't randomly scattered. They grouped into 2 distinct clusters with mysterious gaps between them. Something deeper is going on. Something we still don't fully understand. Scientists are now diving into the impact physics to figure out what hidden forces might have shaped that pattern. And here's where it gets even more eerie. This isn't the first time the DART aftermath has thrown us curveballs. In April 2024, researchers discovered that some of the biggest boulders might actually be on course to hit Mars in about 6,000 years. If that's true, it could threaten any future human colonies that try to settle there. Then in August last year, another simulation based on LISA-cube data suggested that some of the smaller fragments could drift back toward Earth in roughly 30 years. Not dangerous, but enough to create a spectacular meteor shower. So yes, DART proved we can nudge an asteroid, but it also showed just how chaotic space physics really is when theory meets reality. Asteroids aren't smooth or simple. They're rough, unpredictable, and full of surprises. Equations might work on a whiteboard, but once you throw real rocks into space, all bets are off. That's why the ESA's Hera mission is now crucial. Hera is a follow-up spacecraft currently making its way to the Didymos-Dimorphos system, set to arrive in late 2026. But unlike DART, which hit and observed from afar, Hera will stay up close and personal. It'll map Dimorphos in ultra-high detail, measure the crater, study the debris, and see exactly how the asteroid's orbit evolved over time. Hera's mission is about the truth on the ground, verifying what DART started and what LICIA cube witnessed. It'll test every prediction, correct every model, and finally show us whether those fast-flying fragments kept behaving strangely even years after impact. Because here's the deal, we can't rely on one experiment to defend an entire planet. Every asteroid is unique. Some dusty, some icy, some covered in monster-sized boulders. Each one will react differently, and that means every mission counts. If humanity ever needs to stop a real city killer from heading our way, the lessons from DART and Hera could make the difference between disaster and survival. So what do you think? Are we truly ready for the next big space threat? Hit that like button, subscribe for more cosmic breakdowns, and I'll see you in the next one.